Okay, so the next part that we have here is basically exercise 1.1. So let's see what we have here. So exercise 1.1. So exercise number 1 is basically determine whether each of the following relations are reflexive, symmetric, and transitive. So you want to know whether these relations are equivalence relations, meaning that they are reflexive, symmetric, and transitive. Reflexive, symmetric, and transitive. Right. Now, number 1, you have part 1 of this question is you have a relation R in the set. You have a relation R. You have a relation R in the set A is equal to 1, 2, 3, and all the way up to 13 and 14. Defined as R is equal to all the ordered pairs x comma y, such that 3x minus y is equal to 0. So 3x minus y is equal to 0. That means that basically y is always equal to 3x. If you write 3x minus y is equal to 0, then basically 3x, take y to the other side, y is equal to 3x. That means that y is always 3 times x. Right? So what that means is that basically now, in order to decide whether R is basically to decide whether R is reflexive, the condition for that is that basically for every A belonging to the set A comma A belongs to R. If that is the case, you can say that if that is the case, then R is reflexive. That is the condition, right? So what that means is that now in this case, as you can see, for every A belonging to the set A comma A belongs to R, that's not possible here, because in every case, basically every ordered pair that belongs to R, based on the condition that we have here, y is always basically 3 times x, meaning that y and x can never be the same values. Which means that basically R is not reflexive. Which means that R is not reflexive. Now let me take a look at the solutions here. .1. Not sure if this is okay. So now we basically established that R is not reflexive. Now to decide whether R is basically symmetric, basically the condition is that if for every basically A and B belonging to A comma B belonging to the set R implies that B comma A also belongs to R, right? So that is the condition for R to be symmetric, meaning that if A and B belong to A, now if there is an ordered pair A comma B that belongs to R, then B comma A must also belong to R. If that is the case, then basically you can call R symmetric. And in this case you can see that basically all of these ordered pairs that we are talking about, X and Y, in the case of all of those ordered pairs, Y is always 3 times X. Meaning that you would get all of these ordered pairs as basically 1 comma 3 and 1 comma 3, for example 2 comma 6, and so 3 times X is equal to Y. Okay, so 2 comma 6 or 3 comma for example 9, and so on and so forth. These are some members of R. Now of course you can see that over here 1 comma 3 belongs to R, but 3 comma 1 does not belong to R because basically 3 times 3 is equal to 9, and Y is not equal to 9 here. Y is equal to 1. And therefore you can say that 3 comma 1 does not belong to R. Which means that basically R is not symmetric. Right? Now the next part that we have over here, we want to show whether R is reflexive, symmetric, and transitive. Whether R is transitive. Now the condition for transitivity of R is that if basically for all A, B, and C belonging to the set A, if basically A comma B belongs to R and B comma C also belongs to R, then A comma C also belongs to R. That is the condition, right? Now over here, as you can see, so we said that basically all of the ordered pairs that we have here are, for example, 1 comma 3 and 2 comma 6 and 3 comma 6, 3 comma 9, for example, 4 comma, for example, 12, and 5 comma 15, which is not a part of here because you have to stop at 14, right? So now you can see that, for example, 1 comma 3 belongs to R, 3 comma 9 belongs to R, but then 1 comma 9 does not belong to R. So you can see that 1 comma 3 does belong to R, and also 3 comma 9 does belong to R, but 1 comma 9 does not belong to R. So if you use one counter example, it's enough to show that basically R is not transitive, right? But then if you want to show that basically R is actually transitive, then you have to show all the cases, all the possible cases, using logic, meaning that then you cannot basically check a couple of values and say that basically R is transitive in this case, and is transitive in this case, and in this case, and so based on these 3 cases I can say that R is transitive. That it just doesn't work that way, because there might be one case, even if you showed, for example, 1,000 cases, there might be one single case that would prove that R is not transitive. So if you can basically find one counter example, and that would be enough, of course, more than enough. Well, one would be enough. If you can find one counter example that shows that R is not transitive, that means that R is not transitive. If you want to show that, on the other hand, that R is transitive, it's not basically enough to show even 1,000 cases which would prove that R was actually transitive. You would have to use logic in order to show that R in all possible cases would be transitive, and then that would logically prove that R was actually transitive. So then based on this counter example, I can say that therefore basically R is not transitive. R is not transitive, right? So part one of question number 1, you can say that it's neither reflexive nor symmetric nor so you can say that therefore R is neither symmetric nor transitive nor reflexive. Right, so that is basically part 1 of question number 1. Now part 2 of question number 1 is part 2 of question of exercise 1 So the question is basically, we have a relation R in the set N of natural numbers. We have a relation a relation R. We have a relation R in the set N of natural numbers defined as R is equal to all the ordered sets x comma y, such that y is equal to x plus 5 and x is less than 4. And x is less than 4. So let's see how we can solve this problem. Okay, so about part 2 of question of exercise number 1. Okay, so about part 2 of this question. So basically what we have here is basically so we are saying that basically there is some relation R in the set N of basically the set of natural numbers defined as R is equal to all the ordered pairs x comma y such that y is equal to x plus 5 and x is less than 4, which means that basically you have basically you have all of these ordered pairs as, for example, R is equal to, you're saying that x is less than 5, so I'm sorry, x is less than 4, which means that you can start from 1 and then 1 plus 5 is equal to 6, and then you have, if x is equal to 2, then you have 2 plus 5 is equal to 7, and if x is equal to 3, then 3 plus 5 is equal to 8. So that is your R. Now, so which means that basically R is basically contains only 3 ordered pairs, and these are the 3 ordered pairs that R contains, right? Now, 1, 6, 2, 7, 3, 8. Now, basically, what we want to check here for exercise number 1 is that is if basically this relation is reflexive, transitive, and symmetric, right? So for the case that if the relation is reflexive, for that case, basically say that basically for every basically A belonging to the set A comma A has to belong to R. And for example, you can see that for instance, basically 1 comma A does not belong to R. Of course, you can see, of course, you know that 1 does belong to the set N, right? And 1 comma 1 does not belong to R, which means that R is not reflexive. R is not reflexive. Now, for the case that if basically R is symmetric, say that for every, not for every, but for basically if A comma B belongs to R, for example, then if that is the case, then B comma A has to belong to R as well, for all A and B belonging to the set A, for example, right? So over here you can see that, for example, 1 comma 6 does belong to R, but 6 comma 1 does not belong to R, and therefore R is not symmetric. R is not symmetric. For the case that if R is transitive, so basically you can see that, for example, you can say that 1 comma 6 does well, you can argue that since there is no pair in R, you can say that since, for example, if I were to give you a counter example, I would say that, for example, 1, 6 belongs to R, but there is no element in R such that basically that element has the form, for example, 6, for example, some B. 6, B. And what are we doing here? Set of natural numbers, B being, for example, B being any natural number. Any natural number. Therefore, so we said that 1, 6 does belong to R, but there is no element in R such that that element has the form 6, B, for example, B being any natural number. Therefore, any element like 1, B cannot belong to R. And so basically R is not transitive. R is not transitive. Now, and of course you can say that this is true of any of the elements of the set R. This is true of any elements of the set R, of R basically. Right? So that is that. So R is not transitive. But if you want to express that in a better way, you can say that since there is no pair in R, such that X, Y and Y, Z belong to R, then X, Z cannot belong to R. Right? So and therefore R is not transitive. Now this is of course, this argument is based on the condition that we have. That we say that, based on the condition or based on the definition that we have, that we say that R is transitive. If basically if this statement is true, meaning that over here X, Y belongs to R, belongs to R, and also y comma z belongs to R. So if this statement implies that y comma z belongs to R, y comma z belongs to R. So if the following statement is true, now I can say that this statement is true if I think of this statement as, for example, having basically two component statements, P and Q. If basically this statement is true, if assuming that P is true, we can show that, or we can prove that Q is true. Right? In this case, we cannot make the assumption that P is true, since for any x comma y belonging to the set R, there exists no ordered pair y comma z, for example, y comma z, and therefore the statement is not true. Is not true. So what that means is that I'm saying here that for any x comma y belonging to R, there exists no ordered pair y comma z, meaning that if you take a look at your R here, you see that your R is 1 comma 6, right? So if I take this as x comma y, you have 1 comma 6. If I take this as x comma y, then y comma z would be some ordered pair starting with a 6 and with some other number, for example, some a, for example. But then there is no ordered pair in y that starts with a 6, as you can see here. And if I take 2 comma 7, for example, as x comma y, then there exists no element that starts with a 7 and some other number. That doesn't exist. This doesn't exist either. You see that 7 comma 8 doesn't. Or if I take 3 comma 8 here, if I take 3 comma 8 as x comma y, then there is no ordered pair x comma a in that set, and so the assumption, or basically I suppose this part of this statement, any this part of any implication is called the hypothesis. I'm not really sure about it. I need to look it up. But this part is called the hypothesis. So that means that I cannot assume that the hypothesis is actually true. So then I cannot prove this statement at all, which means that the statement is simply not true. So basically that simply means that R is not transitive, right? Okay, so the third part of this question, we need to use some new space here. Third part of this question is basically relation in R in the set relation R. This is part 3 of question of basically exercise 1. Of exercise 1. So the third part of this question is basically some relation R in the set A is equal to basically 1, 2, 3, 4, 5, and 6, as R is equal to basically all the order pairs x comma y, such that y is divisible by x. Y is divisible by x. Okay. So when you say that, of course you know that basically what it means if y is divisible by x. When you say y is divisible by x, what that means is that y is divisible by x. What that means is that is the same thing as saying x divides y. That means the same thing, which means that, for example, I can say that 8 is divisible by for example 4, because 8 divided by 4 is equal to 2, remainder 0. But then by the same logic, of course, you know that, for example, 5 is not divisible by 2, is not divisible by 2, because basically 5 divided by 2 is equal to 2, remainder 1. 2 times 2 is equal to 4, 4 plus 1 is equal to 5, right? So what that means is that whenever your remainder is 0, then whenever your remainder is 0, then basically the number that you divide by the other number, and this number, by the way, now that we are talking about this number over here, when you divide 8 by 4 and you get that 2 times 4 is equal to 8 and remainder 0, this is your remainder. This is your quotient. This is your this number over here is your basically it's called the dividend. It's called the dividend and this number over here is called the divisor. It's called the divisor. So you divide your dividend by the divisor and you get the quotient and the remainder, right? And I don't want to give you wrong information, so let me actually look this up. I'm not sure about the dividend and the divisor. So as you can see here, this is some page from Wikipedia. So as you can see, this is the dividend, and this is the divisor, and this is the quotient. Okay, so that was not wrong. That was actually right. So whenever you have some dividend, some number that you divide by some other number which is called the divisor, whether the dividend is actually divisible by the divisor or not, you're always getting a quotient, and relative to that quotient you will get some remainder. Whenever this remainder is equal to 0, then that means that the dividend was divisible by the divisor. If the remainder is anything, if the remainder is anything except for 0, then that means that the dividend doesn't go into your divisor evenly. Meaning that, for example, you have 8 balls, 2, 4, 6, and 8 balls. These are 8 balls, and you want to basically divide these balls between among, for example, 4 people, or you want to put these balls into basically 4 bags, right? So this is one bag, this is another bag, this is another bag, and this is another bag. So the first time you put one ball into here, one ball into here, one ball into here, and one ball into here. The second time, what you will do is that you put one ball into here, another ball into here, another ball into here, and another ball into here. So, which means that you could do this process 2 times without failure, and none of the balls is remaining. No balls remaining, right? So when you say no balls remaining, that means that your remainder is 0. Which means that basically 8 is actually divisible by 4. Right? Now, and when you say that you could do this process 2 times exactly, that is your quotient. Okay? Now, there could be a situation where there could be the same situation, but suppose that this time, instead of, for example, 8 balls, I have 7 balls. 2, 4, 6, and 7. I have 7 balls here. And I have the same number of bags, 4 bags. 1, 2, 3, and 4. So if I want to divide them between, if I want to put these balls evenly into these bags, so one ball goes here, another ball goes here, another ball goes here, and another ball goes here. The second time, so this is basically the process could be done 1 time completely. The second time, if I want to start the process, as you can see, I have 4 bags here and 3 balls here, which means that the second time I cannot actually do the process anymore. So I have to stop here. So that means that then I could do the process 1 time, right? And 3 bars are remaining. And 3 bars are remaining. Which means that your remainder is 3. Remainder is equal to 3. Since I could do the process one time, that means that your quotient is equal to 1, and so this is your dividend, this is your divisor, for example. And so since your remainder is some other number other than 0, then you can say that 7 is not divisible by 4. Is not divisible by 4. Okay, so that's the meaning of divisibility. Now let's go back to the problem that we had. Actually need to erase all of these things. Okay, and go back here. So now the question that we are asking is that we have some relation R in this set, and the relation is basically this relation, which says that R is basically the set of all ordered pairs x comma y, such that y is divisible by x. And you want to know whether R is basically reflexive and transitive and symmetric. So that's the question that we want to answer here. Okay, so about this part, so basically, if you want to decide whether R is reflexive, basically what you need to do is, of course, for reflexive, we say that for every A belonging to the set A, then A comma A has to belong to R. And let's see if that's the case. So basically the set R that we have here is basically x comma y such that y is divisible by y, meaning that of course, for example, 1 is divisible by 1, so 1 comma 1 would be there, and then, for example, 2 comma 2 would also be there, and 3 comma 3 would also be there, and 4 comma 4 would also be there, and so on and so forth, which means that for every A belonging to A comma A does actually belong to R, which means that then you can say that well, R is actually reflexive, right? So what that means that this is the condition which is the case in the case of our particular example here. And therefore R is reflexive. So R is reflexive, and if you want to know if R is symmetric, so about symmetric, so we say that if x comma y belongs to the set R, then y comma x also has to belong to R, right? And let me take a look at the actual yes, this is the exact, basically I wanted to see if I was, so I can write it this way. So the way that we originally stated this, we said that if basically A1 comma A2 belongs to R, implies that basically A2 comma A1 belongs to R for all A1 and A2 belonging to A, right? So what that means is that basically when we say if this implies this one, that means that you can say, you can rewrite the same statement if A1 comma A2 belongs to R, then A2 comma A1 belongs to R, right? Belongs to R for all basically A1 and A2 belonging to A. Now, so I can say that if this implies this, or I can say that if this statement here, if this statement is true, I can say if basically, let's just call this statement P, for example. If P is true, then I can say that then basically R is symmetric, right? Now, when you say that if this implies this statement, what that means that if this statement is true, then this statement has to be true as well. Or when you say that if for example, if P is true, and P being basically this whole statement here, so the way that you can check whether this statement is true is that, of course, you can break this statement down into, for example, P and Q, right? And basically then you assume that P is true, basically to check whether let's call this statement R, for example, because I have used P and Q here. To check whether R is true, assume that P is true and prove that Q is true. So if you can do that, meaning that assuming that P is true, if you can prove that Q is true, then that means that the statement R is true, otherwise not. Or basically the same thing, if this statement here implies that basically this statement implies this statement, meaning that if this statement is true, then this statement is also true, then basically you can say that R is symmetric, right? Now, in this particular case, you want to know whether basically if A1 comma A2, when basically if this implies this one. So how do you do that? So you have to take a look at our R here. So basically A is basically this set, and R says that X comma Y such that Y is divisible by X. So for example, So for example, one such ordered pair would be, for example, if y is supposed to be divisible by x, then for example 2, 4 would be one of the ordered pairs belonging to R, because 4 is divisible by 2. Now of course then of course 2, 4. Now let me write it this way. So this would belong to R, of course, because 4 is divisible by 2. Because 4 is divisible by 2, right? But basically 2 is not divisible by 4, meaning that you cannot say basically then 4, 2 does not belong to R, because 2 is not divisible by 4. Is not divisible by 4, right? So as you can see, for example, 2, 4 does belong to R, but 4, 2 does not belong to R, which means that, so basically you can say that 2, 4 does belong to R, but 4, 2 does not belong to R. Which means that, meaning that R is not symmetric. Let me take a look at this solution here. Okay, so the next part is basically whether R is transitive or not. We want to show whether R is transitive, right? So basically the condition for transitivity of R that we use is that we said that if A1, A2 belongs to R, and A2, A3 also belongs to R, implies that A1, A3 does also belong to R for all A1, A2 and A3 belonging to A, right? So that is the condition that we use. Now what that means is that basically so if this statement here implies this statement, right? Meaning that if this is true, then this has to be true as well, which means that this implies this, right? So what that means is that now let's see if that is the case. So basically the set A that we have here is basically this one, and x, y is divisible by x, meaning that I can say that, and in such cases basically if you since you really do not know whether this statement is true or not, meaning that if that is actually the case or not, you don't really know. So then it's usually easier to start with a counter example. And a counter example is that you start basically testing with just one simple case. Meaning that, for example, suppose that 2 comma 4, 2 comma 4, you know that it does belong to R, because 4 is divisible by 2. And also you know that 4 comma 8 also does belong to R. Also does belong to R. And also you know that basically 2 comma 8 does also belong to R, because 8 is divisible by 2 as well. So it seems that that is the case. And I think this is going to happen well. Then you might get into some sort of trouble. I mean, let's go down to the bottom and basically examine this a little bit more closely. So you have 1 through 6 there. So you have A is basically 1, 2, 3, 4, 5, and 6. And R is basically the ordered, all the ordered sets x comma, ordered pairs x comma y, such that y is divisible by x. Such that y is divisible by x, right? Now, well, we had no problem with 2. Now, with 1, of course, any number is divisible by 1, meaning that if I take my x as 1, then I can take 1 with any of these numbers, meaning that 1 with 2, for example, 1 comma 2 does belong to R. And then 2 comma, for example, whatever you take, for example, 2 comma 4 does belong to R as well. And of course 1 comma 4 does also belong to R. 1 comma 4. So we have no problem there. And let's see what happens, for example, with 3, for example, 3 and 6. So you can see that 3 comma 6 does belong to R, right? And then 6 comma now there is no case there, because I have no more numbers than past 6. I have no numbers here. So I would need, for example, some ordered pair, like for example 6 comma 12. If that was the case, that if that belonged to R, and then 3 comma 12 would also belong to R, and then we had no problem there. But that's not the case, right? So which means that basically but that is not a problem. That is actually not a problem, because in this case, when your hypothesis is not true, meaning that if we are saying that this has to imply this one, meaning that if this is not true, then it doesn't really matter if this is true or not. So we have no problem there. So I suppose we are good here, except that, of course, you cannot, except that this is actually not a proof, right? This is not actually a logical proof. So in this case, let me take a look at the example. I'm sorry, let me take a look at the solution. It says that basically, as I suspected, and of course this kind of suspicion is not valid suspicion. I mean you cannot trust it in any way. But it turns out that R is actually transitive, meaning that you can say that let x comma y belong to R, and well, let's say that x comma y and y comma z belong to R, then y is divisible by x and z is divisible by y. So y is divisible by x and z is divisible by y, of course, by the rule that we have, up here. Then y is of course divisible by x and z is divisible by y. And z is divisible by y. So z is divisible by x. Therefore z is divisible by x. And therefore you can say that x comma z belongs to R, right? Which means that R is transitive. This is a proof, right? This is actually a proof. Okay, so now in order to understand how we basically what this means, of course it's not hard to understand what this means, but the important part here is to understand how we came to this conclusion here, which is basically, here we say that, here we make some assumption that x comma y and y comma z belong to R. Okay, so this is some assumption that basically we have made. Now, using this assumption, I can say that y is divisible by x and z is divisible by y, and that is based on, and then this conclusion based on this assumption is based on the rule that we have here, right? So here we say that if x comma y belongs to R, then y has to be divisible by x, right? So basically, so far we have no problem. Now, based on what we have here, basically we have concluded that z is divisible by x, meaning that if y is divisible by x and z is divisible by y, then we can conclude that z is divisible by x. So how can we make that conclusion? So basically, when you say that x comma y belongs to R, what that means is that based on this rule which says that basically if x comma y belongs to R, then y is divisible by x, then what this means is that basically y is divisible by x. And also when we say that basically y comma z belongs to R, then basically based on the same rule we can say that z is divisible by y. Z is divisible by y. So now based on these two, I can conclude that z is divisible by x. Based on these two, I can conclude that z is divisible by x. So how? So let's say that, for example, let's take a couple of numbers for these to make this a little bit simpler. Meaning that, for example, I say that instead of 2 comma x comma y, I take 2 comma 4, and then I write over here 4 comma, for example, 8, right? So when I say that y is divisible by x, what that means is that x is a factor of y. What that means is that x is a factor of y. And when I say that z is divisible by y, that means that y is a factor of z. Y is a factor of z. So So when I say that x is a factor of y, what that means is that, so this 4 over here is y, and this x over here is 2. So I'm saying that x is a factor of y, meaning that if I factorize 4, I will get 2 times 2. So these two are called the factors of 4, because I got these two factors by prime factorizing 4. And over here, basically I'm saying that y is a factor of z, meaning that if I take again the same number, for example, if I take 8 over here and prime factorize it, I get 2 times 4 and then 2 times 2. So 2 and 2 and 2. So all of these factors, including this one, these are basically called factors of 8, right? So since these are factors of 8, you can see that 4 is a factor of 8. You can see that 4 is a factor of 8. So I can refer to 4 as y. I can refer to 4 as y. I can refer to 2 as x. I can refer to 2 over here as x. So here I have x and y, and you can see that x is a factor of y. X is a factor of y. And over here you can see that I can call 4 over here y. I can call this 4y, and I can call this 8z, right? So you can see that 4 is a factor of 8, and then basically you have the same thing over here, meaning that you have 2 2's here, which is basically the same thing over here. So these are basically my x's over here, right? So you have z, y, and x. So which means that when I say that x is a factor of y, which is, as you can see, x is a factor of y here, and when I say that y is a factor of z, which, as you can see, y is actually a factor of z here. What that means is that basically 2 is actually a factor of 8, or x is a factor of z. So then you can say that x is a factor of z, right? Now when you say x is a factor of z, that means that what that means is that basically 8 is a multiple of x, or 8 is a multiple of 2, or you can say that z is a multiple of 4. What that means is that basically, suppose that I have, for example, 15. 15 is the same thing as 3 times 5. So I can call 15 a multiple of 3, or I can call it a multiple of 5, meaning that 15 has 3 or 5 as its factors, meaning that I can write 15 is the same thing as 3 times 5. These are basically the factors, and you can call 15 a multiple of these two numbers, right? So therefore, in this case, I can say that 5 is a factor of 15. 5 is a factor of 15, or I can say that 15 is a multiple of 5, which means that the same thing as 15 is a multiple of 5. So again, using the same logic and understanding, when I say that basically x is a factor of z, then that means that z is a multiple of x. Z is a multiple of x, right? So and of course you know that when z is a multiple of x, what happens is that, for example, let's take the example of 15. 3 times 5. Again, in this example, I can say that 5 is a factor of 15. 5 is a factor of 15. Or I can say that 15 is a multiple of 5, right? So in this situation, as you can see, I can say that basically that number which was a multiple, which was 15, is actually divisible by that factor, because 15 divided by 5 gives me 3, remainder 0. So that means that basically 15 is actually divisible by 5, right? So the number which is the multiple is actually divisible by the factor, but not the other way around, meaning that you cannot say that 5 is divisible by 15. It's actually not divisible, right? So what that means is that when over here, when I say that z is a multiple of x, then I can say that z is divisible by x. Now, if z is divisible by x, what that means is that based on this rule that we had up here we said that all the ordered pairs x comma y such that y is divisible by x. So if y is divisible by x, that means that if z is divisible by x, then x comma z, I apologize, then x comma z belongs to R, because based on the rule that we have in R, we are saying that the second number is divisible by the first number, right? So over here, z is divisible by x, so the second number is divisible by the first number. So then here you can see that you can prove that x comma z, or you can show that x comma z belongs to R, right? So over here we have assumed that x comma y and y comma z belong to R, and then we have showed that basically x comma z does actually belong to R, which means that R is transitive, right? So these are the very basics of mathematics, but of course, as you can see, very important, meaning that, for example, this is essentially only mathematics class 6 or so, class 6 or 7, not even class 7, class 6. It's the basics of numbers. But if you don't understand the basics, then you will get stuck. Mathematics is just simply so. Which means that, well, if you feel that basically there is a whole bunch of things that you don't understand here, that means that you have to go back and see where the problem is. Mathematics is always like that. Okay, so this was basically part 3 of this question. So in the next video we will continue this. I'll see you in the next video.